Thank you, Ada. Let's turn to the part of aluminium. Aluminium is the second most widely specified metal in building, and pure aluminium has a relatively low strength So in the construction industry, aluminium is usually alloyed and anodized before use to improve its strength and corrosion resistance. Architectural and construction projects often incorporate these strengthened materials into their external structures, as they are capable to withstand all types of weathers. The major applications of aluminium is window frames, roofing, sliding, and curtain rolling, etc. Aluminium alloys in general have a high heterogeneous microstructures, which provides high strength in properties. The most important cast aluminium alloy system is the aluminium and silicon, where high levels of silicon 4% to 13% contribute to give good casting characteristics. So the following micrographs are all based on the aluminium with silicon alloys. The three very common microstructures include the single-phase microstructure, two-phase microstructure, single-phase microstructure with intermetallic particles. In the single-phase microstructure, when the melt aluminium alloys has a content of silicon less than 1.65 weight%, the microstructure has a homogeneous grain structure, which different size of grains dependent on the undercooling and the solidification time. In the grain refinement, a fine microstructure can be attained, and with a fine microstructure, higher strength and toughness can be result. And the above micrographs is the grain size of larger grain size, and the below one is the fine grain size microstructure. The two-phase microstructure is obtained when the alloy is hypoelectric. An alloy with silicon content between 1.65 to 12.6 weight% will be the two-phase. The two-phase microstructure, where the primary A aluminium crystal are distributed in the eclectic phase as seen in the figure, and has a low melting point of 5077 degrees Celsius. Aluminium and silicon have no solid solubility below the eclectic, and microstructure solidifies as silicon particles in an aluminium matrix. The precipitate phase acts as an obstacle to the motion of dislocations through the aluminium matrix, thus raising the yield strength inversely proportional to the interparticle spacing. Single-phase microstructure with intermetallic particles is found in heat-treatable aluminium alloys, filled the 2000 series, which is the alloy with copper. And the intermetallic particles can be found in the grain boundaries. And the supersaturated hardening precipitates leads to high strength in the alloys. Intermetallic compounds have low ductility and low electrical conductivity because of the non-metallic in behavior with the ionic or covalent atomic bonding. Let's turn to the microstructure of anodized aluminium. Anodizing of aluminium can generate a porous surface oxide film. Typically in the building industry, thickness of films are 5 micrometers to 25 micrometers. Depends on different applications. The thickness of films are controlled by anodizing conditions. The thick outer coating produced, along with proper sealing, increases the corrosion resistance of the surface as it prevents further oxidation. In terms of strength, The anodic layer is extremely hot, usually between 60 to 70 Rockwell C. It is the second hottest following the diamonds with respect to its hard crystalline structure. The porous structure also facilitates the high absorption and penetration by colored dyes. Different degrees of light fatness will be results from different dyes and pigments. So some of the dye aluminium alloy are good finishes for outdoor exposure. Aluminium is opaque. It is not transparent because the incident radiation having frequency within the visible range excites electrons into unoccupied energy states above the Fermi energy in accordance. The incident radiation is absorbed by near-surface electrons, and the continuously available empty electron states allow all frequencies of visible lights to be absorbed by metals. And this is also because of the continuously available of empty electron states, and which permits electron transmission. In terms of the reflectivity, aluminum will reflect 90% of the absorbed radiation from the surface and appears as reflected light. A bright silvery appearance results when exposed to white light over the entire range of visible spectrum. In terms of transmission of light, only metallic films thinner than 0.1 micrometers are capable for transmitting the visible light. For anodized aluminium, the optical properties of it is highly dependent upon its anodizing process used. After anodizing, the average transmittance of visible light is found to be close to that of the glass substrate and increase with the anodizing time. As the aluminum is completely converted into oxide, the average transmittance of the anodic aluminium film which is about 78%, and a higher refractive index is recorded increase with the anodizing time. In infrared, Mondelov indicates that our reflectivity of smooth aluminum surface is 94% to 99% from near to far infrared. Highest reflectivity is obtained by vapor disposition, which can produce very smooth surface. The reflecting power of aluminum surface decreases with roughness, and sandblast aluminum surface may to be only 15 to 20% for the liquid state. The highly polished 99.99 aluminum is recorded to have a 1% at 180 K and 1.8% at 290 K. In terms of the environmental performance, in anodized aluminium, the anodic films can be produced in color by variety of methods. While many of the colors are extremely light fast, carriers have to be packed in colors produced using organic dyes or pigments which will be degraded by the ultraviolet. The high energy ultraviolet rays could break the chemical bonds of colored molecules. This is in turn alters the shape of molecules, destroying the parts of the molecules that contribute to coloring. When more and more molecules are reacting with the UV, and so there will be fewer molecules that have not reacted or decolorized. And so this causes the overall color fade over time when they are exposed to sunlight. Meanwhile, as the color is the result of light wavelength scatter and reflection in the anodic film, the electrolytic coloring, the two-step electrolytic methods produce coloring which is unaffected by the ultraviolet rays, and so it is much more suitable for external use. To minimize the decoloring of the interior use of organic dye aluminium, it is important to control its exposure from UV. Daylight filters should be placed in laminated glass. Besides, solar films can be applied to reduce transmittance of UV radiation. In areas with moderate temperature, furnitures containing UV absorbers can be painted onto the inside of window glass. In addition to all the filters, thin blinds and curtains can be applied to minimize the UV contact with interior aluminium use. Then I will pass the time to Becky to talk about the properties of copper.